Hello, everybody, and welcome to our today's IDS Vision Channel session. I hope you had a good summer break and you used also to have a look on our summer special topics in the IDS Vision Channel. Today, we have the topic about smart city. Smart city is a highly exciting field. I think it's in all the newspapers, it's in all the things you read at the moment, what could be made more smarter in our cities. Similar to the industry, digitalization is bringing many new opportunities for making lives in cities and communities more efficient, more sustainable, and even more attractive. Here, too, it is a matter, for example, of expanding existing infrastructure and personal intent processes, reducing costs and promoting local economic competition. With the rise of advanced technologies such as the Internet of Things, as well as the introduction of computer vision, edge computing, machine learning, artificial intelligence, and most recently 5G communication networks, the necessary tools are now available for transition to smart cities supported by digital technology. We as a camera manufacturer are of course very interested in solutions with intelligent image or video analytics to achieve these goals. But especially in the public sector, the issue of data protection plays a major role in image-based evaluations. A topic that definitely raises many questions as well as many possibilities. That's why we have today invited 3 companies which want to show us possibilities, solutions, and also challenges of vision-based AI for smart cities. And they're also here to answer all your questions. But before we start, let me do some housekeeping stuff. During the session, please, if you have questions, put them in the Q&A section below of your Zoom client, and we will answer then or try to answer the questions after each session. And in the end of the session, we will have a plenary discussion where we also grab some open questions. So if you have questions, please type them into the Q&A section. Myself, I'm Patrick Schick. I'm Product Marketing Manager here at IDS, and I will be the housekeeper of today's session. So I will moderate the session and I will take your questions and ask the presenter. I will be also the timekeeper so that we have a look that every session will take around about 20 minutes with Q&A afterwards. Also, for your information, the session will be recorded, and after the live session, it will go into our media library so that you even want to recheck some point we've discussed here. Just come to our IDS Vision Channel media library and have a look there for this session. But I think that's all for now. I would like to introduce the first speaker. It is Dominik Nestler from the Bochum-based company Centene, and he has already managed various computer vision projects and is looking forward to share his experience with the community. Today, he tells us about predictive maintenance of road infrastructure. So Dominik, the stage is yours. Share your screen and go ahead.
All right, Patrick, thank you very much for the introduction and the warm words for welcome. Let's see. Yeah, there we go. That looks good. Hope you can all see the screen. Just gonna move that over here. All right. So short thumbs up, Patrick. Can you see the screen?
Yeah, perfect. Screen can be seen.
All right. Perfect. Well then, hello everyone, and welcome to my talk today about the analyzing street sceneries and how that leads to a predictive maintenance of roads. And first of all, again, thank you for EDS, for Patrick, for hosting this great channel and those series of events. We're very happy to be part of this, and I'm very happy to present to you today and excited for all the questions that there may be. Before we start and get into the presentation, let me briefly introduce myself and why I'm here today to talk to you about computer vision in smart cities. My name is Dominik Nessler, and I have a master's degree in sales engineering and product management. And before working at a tech startup in the field of AI, I worked in business development and as project manager for global tech companies like Audi or Bosch. And currently, I'm in the position of head of sales here at Sentin. A few words about Sentin. We are a service provider for software and AI solution based in Bochum, Germany. And for building our solutions, we use our own developed software tool, which is called Sentin Explorer, which we will also see today as we are going through the presentation. The Explorer is a platform for all of our projects to build suitable data sets, annotate data, as well as run and manage and retrain the AI models that we develop with and for our customers. For today's talk, I have three smart city use cases actually that we have worked on in the past or are currently working on. One of them is monitoring and inspecting building in cities using image feeds from drones. This is, for example, relevant for insurance companies or local authorities to assess damages on buildings after severe weather conditions. Also to assess whether public buildings are in good condition or renovation works needs to be initiated even before major damages occur, or whether illegal and unauthorized construction work has been done on buildings. This use case is really what represents the great benefits of smart cities, because it brings together two innovative technologies that open up new possibilities. With the mobility and flexibility of the drone, it is easy to even get to hard to reach parts of a building or construction sites and can be reached. And then on top of that, computer vision solutions can quickly analyze the sceneries. The second use case is the road condition monitoring, and it's used for like real-time citywide data to measure road quality and identify road deterioration before dangerous and costly road hazards sprout on the streets. The challenge many local authorities are facing when it comes to road damage, and you probably all know that from your daily commute to work or to the gym, hitting potholes. It is that they have a underfunded budget. For example, I did some research before that, and I had to dig a little bit into the past and found a report that was back in 2014 for our hometown here, Bochum. And for example, Bochum is missing around 5 million euros yearly for repairing and maintaining the infrastructure. And if you add that to the reports from the German Federal Ministry of Transportation and Digital Infrastructure, that shows that in the last 5 years, the cost for maintenance of roads increased by 41% just due to the aging building structure. So if you combine the missing 5 million in 2014 and then increasing expenses due to the aging building structure, the only path forward is to do more with the existing budgets in a proactive and preventive way, and that is analyzing damages before they occur and do the repairs. It's a little bit with the healthcare prevention, where prevention is the best treatment. Earlier road repairs prior to large and more comprehensive repairs are proven to extend the useful life of roads while saving up to 30% of the costs. So that's a huge upside if we take that into account and use the technologies available. And finally, our evergreen when it comes to smart city, it's closely linked to the use case before, and it's the anonymization of personal data on street sceneries. In both use cases, it's nearly impossible not to capture people walking by or cars being parked on the street. And to further use these images to display results or to do further analysis, we need to anonymize faces and plates to comply with the GDPR protocol. And those are the three use cases that we're going to see during the presentation today, and going to be our practical guidance throughout the talk. To start off, I'd also like to clear up one misconception that sits in many people's minds when it comes to the topic of AI or computer vision in industrial applications. Many people when it comes to AI, think of the big players such as Google and Amazon, Facebook, and Tesla self-driving cars. Those companies accomplish almost impossible things with their technologies, but what many tend to forget is that those developments does not happen overnight. It takes huge data sets, which have been built up over years or in extremely costly projects. So developing and working on or with AI solution is not like flipping a light switch. It's inherent in this technology that it does not work to implement it at the push of a button. To create even generalized models, millions of data are needed. And this amount of data is simply not available or accessible in many industries. Therefore, the real key to work with AI and to start working with AI is having a structured approach to build and implement applications for use cases over time. And maybe some of you ask, how does this process look like? And it can look like somewhat like this. And this is how we have done it in the past. So looking back at the experience we've gained from working on different computer vision projects. So these 6 steps more or less have emerged as a recurring pattern when it comes to setting up AI solutions. So let's walk through the single steps real quick in theory before we take a look at what that means for the use cases I explained earlier. So first step is collecting data. And today I'm not going to tell you that data is the new gold or oil. Most of you know by now. What I want to emphasize when it comes to collect data is the question, do I have the data it takes for implementing the solution I want, or can I generate such data? It is very important to get an understanding of what kind of information is actually represented in your data. The question you need to ask yourself is not only how much data do I have, but also do I know, or do I have the right distribution of different defect classes in the data set? And do I have enough data for what I want from a solution, or do I need to set smaller targets first? And even by just taking a closer look at your data and asking you all those questions, you can already gain massive insights without any line of code or AI. Next step would be data preparation. Once the data set is cleaned and is set up, it is time to enhance the data with the additional information being used for the training process. Most of the time, this process is also referred to as annotation or image labeling. In a few minutes, I'm going to show you different ways to label your data and why it is crucial to choose the right annotation format and process. Next up is model training. So based on the desired outcome, one can choose from different models. I prepared a little slide here to show the difference for those of you who don't know and for those of you who already know. I hope I'm not going to bore you. First of all, there's the pure classification of image content. Here it's pretty simple on a simple example. Are there certain objects in an image? In this example, it could be investigated whether there are balloons in the image or not. Of course, it is possible, or possible applications in industrial contexts are almost limitless here. For example, we can take a look at a certain defect is visible in an image and classify the image accordingly to different acceptance classes. The drone use case I'm going to show you later, for example, is a classification use case. The next level of algorithm is a little bit more distinctive. With an object detection, one can distinguish different objects on an image and, for example, count the balloons in the image instead of just classifying, do we have balloons or not? The next model up is the semantic segmentation, and this basically involves analyzing the image pixel by pixel and looking to see what is on those pixels. So in this case, we can determine if a pixel is a balloon or is not a balloon, and therefore could locate the balloons in the image. And then the most sophisticated model type is the instance segmentation. And the instance segmentation basically is determined or is used to determine how large individual components are and analyze them individually. So in contrast to semantic segmentation, the balloons are not recognized and analyzed as a single unit, but a distinction is made between each and every balloon, so the individual balloons in the picture, so that we could evaluate how big one of the balloons is and how much area or how much of the area it occupies. So those are the different type of models that we can train, and also the I mentioned before, the annotation for those different type of models is a little bit different, as we're gonna see later on. And then let's head back to our 6th step here. So finished model training, next up is validation. And for this process step, I want to introduce to you the ground truth. Ground truth is the one-to-one description of the data set that should be used for training, testing, and validation purposes. Or to put it in other words, a conclusion should be determined by process expert about the indication and associated metadata presented in the test data and the training data. Why is the ground truth so important? By defining which defects are present in a data set, it becomes possible to evaluate and validate the performance of the system. And I can compare how accurate the detection of defects or objects actually is and what limitations there may be. And then next up is integration, monitoring, adapt, and retrain. This process is very individual and depends on different aspects. So this process step is where the AI is transferred from the development environment to the productive solution. And during the integration, it is most of the time it's very important just to link the AI system with the existing system and software, for example, for archiving data or integrated into existing workflows in the best way possible. What is also very important here is just to continuously monitor the solution so that due to domain shifts in the images, performance can fluctuate also with AI. There is a chance that there's performance drop just when the image scenery completely changed, or you have a new type of defect that you haven't used for training before. So therefore, the ground truth should be extended by new image data at regular intervals, and continuously your solution should be tested so that if fluctuations occur, that the critical images can be identified and put into or reintroduced into a retraining process, so that the operation and optimization of an AI solution, like I mentioned earlier, is not like a one-time task, but a continuous and iterative process. All right, one quick side fact here. We all believe in the technology of AI in computer vision, otherwise we wouldn't be here today, right? But how come that we don't really see the technology flourish in industrial use cases yet? Well, at least we see some hurdles here we have to take. Maybe someone would say or think that is because the model training fails or the technology maybe is not sophisticated enough. However, this is not the case, because studies have shown that 8 out of 10 AI-related projects in industry fail because the available data is not sufficient enough to get the desired outcome. Just to give you something to think about as a little remark, and closing with that, I would like to take you through the 3 use cases. And yeah, let's start with the first step of our process, and this is collecting images. And yeah, first step, as I mentioned, collecting images. And as you can see, for the various use cases I mentioned, the image material on the slide looks very, very different. So most of the time, the question is, what are the requirements for the image? What type of camera do I need? What resolution? Which angle should be the position, the camera be positioned? And there's no definite answer to this question. That a certain megapixel camera has to be used or is required for acquiring images. Some of the images on the slides are at the basis for the project. Or some of the slides, pictures on the slide are actually taken by a smartphone. So the answer to what type of camera do I need is really hard to answer. So the rule of thumb for image quality basically is that the image is good enough if we as a human being are able to see and detect the characteristics we are looking for on that image. So second big question that is probably also on your mind is how many images does it take to train an AI so that it's properly working or proper working? The answer to this question is very simple. It depends on your use case and what your desired output is. It's not a problem to train an algorithm with as little as 50 images. However, you have to be aware that you might have a significant drop in performance if you start to change the scenery. So the reliability and the robustness that makes the use of AI so valuable can only be achieved using big data sets. And that robustness is very important for our use cases here, because as you can see on the images, we have a number of variables that have to be taken into account when analyzing the images. So we have different times of the day. So we have a rather bright lighting situation during the day, low light during the night. We have cloudy weather, sunny weather, we have rain, we have fog. So for those type of use cases, you rather need bigger data sets. For the smart city use cases we are looking at, we have for the road condition monitoring, we currently have 17,000 images that we use. For the drone use case, for the monitoring of buildings, we have around 280 image. And for the anonymization of face and plates, so our incognito, we have 50,000 images. So you see how it also varies depending on what your desired output is, whether you really need a classification like for the drone use case, or if you need a more sophisticated model to really detect those faces and plates spot on to just anonymize them. So rather more images than less. One last word about collecting in the amount of collecting data and the amount of data. Not in every case you need big amount of data sets to configure an AI-based solution. If your solution provider already has existing algorithms that are trained to detect certain things in an image, and you want to detect the same things on an image, you can build on existing solutions. And then that even 50 images can be enough to get a robust solution. So let's take our use cases, for example. Let's say we take the drone use cases and you don't want to inspect roof buildings, but want to inspect something similar, or even want to inspect roof buildings, but they look different than what we have in the use case before. Then there's a high chance, or it's very likely, that we can use your data with the existing model and get a good result with even as little as 50 images. All right, now let's take a look into the software and what data preparation actually looks like. As I mentioned, the drone use case, which we are looking at here, is a classification use case. So in order to prepare the data, we have to assign classes to the single images. So in this use case, it's very simple. We have two classes. We have issue and no issue. So we evaluate every image by hand, basically, and just select whether we see an issue or do not see an issue on the image. And this is how the data preparation works for a classification model. All right, this is data preparation again, but now we're not trying to just classify images. We want to use an object detection to really detect certain objects in image. So what we do is we draw bounding boxes around the objects that matter to us in the image, and then we label them. In this case, it would be plates and faces in the scenery. And now we will just go ahead and select all the faces and plates in this scenery. And this is what data preparation looks like in order to get an object detection model. So in this case, later on, we could detect all the plates and faces in the images, and the feedback from the system would be exactly those bounding boxes. Let's move ahead. And now this is the preparation for the road condition monitoring. In this use case, we have a segmentation. So here you can also see the software. We just select a folder with an example image right here. And in order to do a segmentation, it is not enough to use bounding boxes. What we do here is we try to capture the defect, in this case, the potholes, as narrow as neat as possible. And so that we really, in this case, later on, can measure the length and the width, for example, of the pothole. And as you can see here, we have to go very into detail for those smaller objects right here. And for this, we use a polygon segmentation to label, enhance the images, to use them later on for the model training. All right, so now in theory, we have done it for a couple of thousand of images, right? And we have either done the classification, or we have done the object detection, or the segmentation. And now let's see what it looks like if we integrate them and execute those models. So I just have a random image here, street scenery, and then here in the drop-down menu of our tool, you see the different type of AI models that we have integrated into the software environment. So let's say you have your own use cases, different use cases. You can integrate different type of AI models within the solution and use them to analyze your images. So in this case, I'm gonna select a common image classification. So what we wanna do now is we wanna classify the image and get a feedback on what is actually or in the image. So we selected the model, hit evaluate here, and then we get a feedback. And what we can see, we have a crash helmet, we have a moped, and we have a scooter. So again, this is not specially trained for those images. It's just an example on how that works on different type of images. Now we switch to another AI model. We select an object detection, hit evaluate again, and now we get those bounding boxes back, and we get a label for a car, or identify this one as a truck. And this is basically the difference for you to see between classification and an object detection. And again, those are just on common objects. And then let's go ahead. For example, if we click fill, this is exactly how the anonymization would work. We could now use that to basically blur the cars on the image. And then last but not least, we're gonna delete those annotations here. And now we're gonna switch from the object detection to a segmentation. Remember where we drew the single lines around, or the very narrow lines around the objects we want to detect. And now again, we get the feedback that we have cars and trucks on the images, but as a difference to the way before, now we have a very, very neat outline of the car here. And we could use that information, for example, to now calculate how big or how many pixels are within this annotation. And for example, how big is that car in relation to other cars? So those are the different type of models that you can train. I showed you how you could annotate the data set for that. And then last but not least, I want to show you the incognito one more time. So this is the smart city use case, one of them I mentioned. So that's the face and plate detection. Just select it here. And now, as you can see, we have a bunch of images and we do not need to evaluate all of them one by one. We can just start a batch process for that. And then it's going to go through all the single images. You can see that down there. And then we can just click into one to see what it detected. And that's actually what it looks like. We get a feedback on all the plates. We have filled the labels so that we don't see them. If we skip to the next images, here we have a plate down here and a bunch of faces that are all detected and filled the boxes so that we can anonymize the scenery here. And this is basically how our smart city use cases work, or at least some of them. Happy to reach out and can also demonstrate the other use cases we have. This is one of them. And also how the different steps are in theory and a little bit practical guidance there on how we do that using our software tooling, the Sentinel Explorer. And yeah, I hope I'm not too much over my time limit here. And thank you very much for paying attention.
Thank you, Dominic, for this interesting talk. So the audience, now is your time to ask questions. Just use the Q&A section in your Zoom client. So till the questions are coming in, I would have a question which I always have when I see such application solved with artificial intelligence. So there is for me always a question: why does it need AI to solve this applications? Is this only solvable with artificial intelligence, or could this be also rule-based?
Yeah, this is actually a good question, and a question you should always ask yourself before approaching AI. Does it really need AI? But let me give you the example of the pothole that we saw in the short video. You can imagine that we have different kind of surfaces that look different. We have maybe something like concrete surfaces or other type of road surfaces, and also the potholes look different each and every time, so pretty much unique, and would be very, very hard to find rule-based rules to describe potholes on different sceneries. So that's one example why AI is really good for those use cases, because we can just use sample images or example images and teach the system to detect certain characteristics that would be very, very hard to describe with rule-based algorithms.
Okay, thanks. That is right. And there's another question. So in general, not directly a technical aspect. So have you already deal or struggle with reservations regards camera surveillance in this case? And the second question comes with it. How do you communicate as all the information is anonymization and with the personal data?
Yeah, that's always a big issue. There's surveillance aspects of it. So what we basically do is we show people how it works and that it actually works and the way it works. So we use basically the sample images that you have seen today, and we just show people, partners, clients, hands-on that it is reliable and that it works. And also the way we built the architecture for this specific use case, the image data that comes in that is not anonymized is not stored permanently. So the images goes in and we get the anonymized as a feedback, and the other image is not stored on any of our servers or anything. So that's how we try to resolve those issues there.
Okay, perfect, thanks. So we have two other questions before we go to the next speaker. One of it would Can you elaborate more on the point you made? Data often not sufficient yet to enable flourishing industrial applications?
Yeah. So the data sets often do not really represent what the client wants or client needs. So for example, we really like have the use case that or application that customers are sending us their example images with defects on them, for example, and then they want to have them measured, and that is possible, but we always need like a reference within the image to know exactly how much centimeters, millimeters 1 pixel represents. So most of the time, or in some cases, the data is just not sufficient enough in a way that it has not all the information that we need to use for AI, because the way that works is not that there's some magic working in the background that knows it all. So really have to have all the information need to be in the image, or we need to enhance the image with the information in the labeling process, for example. And the other thing is it's always about a little bit about the amount of data. So let's say I only produce 50 parts and 2 of them are scrap. So I only have 2 example images of scrap parts. It's hard to, just collect the amount of data you need to actually train an AI. And this also goes back to your question before, does it always need AI? In some cases, it just does not need AI, and rule-based algorithms are still the way to go, especially if I don't have the right data set for it. But whoever asked the question, we're happy to elaborate about that later on. Just reach out and we see if you have a data set and are not sure if it's sufficient enough. Let's take a look at it and see if that works for you.
Perfect. Then, thanks. The last question, it's more going to technical. So which kind of camera are you using for the AI application? And are you using TPU or NVIDIA Edge?
We're using TPU to answer that question. And camera are really different. On the drone use case, I actually do not know what kind of camera was mounted on the drones. For the road condition monitoring, we're actually using smartphone images at this moment to start the first prototype. And then the last one, the anonymization, I think was a full HD camera that was mounted on top of a service vehicle, but I don't know the exact camera type. But it was a full HD camera that was capturing the street sceneries there.
Okay, thanks.